Hi guys, Levi here from Bright Young Brains. Today we're going through grade 12 cubic functions. So you will note in most of the content that we cover, we'll always specify what level it's on, especially now that we're going to be working on differential calculus and cubic functions. So we know these are the kinds of topics which you will also find yourselves going through in varsity, right? However, the level is slightly different, right? So on our side with cubic functions, one major thing that we all want to remember is the standard form of our cubic functions, right? So this is the standard form of our cubic function. We have already touched on the standard form in terms of how to solve for x on the solving for cubic functions series that we recently just had. So if you have not gotten a chance to have a look at that, I would recommend you take some time to go through those, because for you to be able to understand cubic functions in terms of sketching them and working with them, you definitely want to be very comfortable with solving for x when you have equations that have an exponent of 3 or a degree of 3, right? So with our cubic function, one key thing we want to remember about a cubic function is we say it is the standard form. The other main idea is the standard picture, or rather the sketch or the rough idea of what a cubic function looks like. So if you've been going through your textbooks, in terms of a cubic function, this is what you have. Something like this, right? So this is a cubic function. A cubic function in this manner, right, will generally have an a value that is bigger than 0. So what we mean by that is, can you see that this graph basically goes up, comes down, and then goes up indefinitely, right? So anytime we see that trend, we know that the a value is a positive. So in terms of us keeping in mind cubic functions where a is a positive, we know that this is like one of our scenarios, right? This is one scenario where we have 3 x-intercepts. 1, 2, 3, right? What we want to keep in mind though is, even though we will have cases where a is bigger than 0, this is not always the picture in terms of our x-intercepts. We have 2 more cases. This is one of our other cases, and as you can see, we have 2 x-intercepts there. And then the last one, we only have 1 x-intercept. So what you can think to yourself is, as you move your cubic graph up, right, here we have all 3 x-intercepts, and then as you move it up, eventually it's only going to have 2 x-intercepts. And then if you keep moving it up, eventually it only has 1 x-intercept. So this is like the minimum number of x-intercepts your cubic graph will have. And key thing is, your cubic graphs will always have x-intercepts. You don't have a cubic graph that does not have an x-intercept, unless you maybe have restricted the domain or anything like that. But for the scope of this tutorial, or the scope of grade 12 rather, and cubic functions, you know that you will always have at least 1 x-intercept. And then key thing is also to note that with all our 3 graphs, we at least have 1 y-intercept for each of them, and we can have at most 3 x-intercepts, and we can have at least 1 x-intercept. So this is all going for cases where your a value is positive. So for cases where you have your a value as a negative, we know that your graphs will start by going down, and then eventually they'll go down indefinitely, right? So anytime you see your a value as a negative, this is the picture you want to think of, one of these, right? Depending on what your equation looks like. And again, you will either have 3 x-intercepts, 2 x-intercepts, or 1 x-intercept. And this all depends on what values are in your standard form, right? So just like when we work with the parabola, we know that with the parabola, if your a is a positive, you have like a smiling face. If your a is a negative, you have like a frowning face. So things like that, we know that for a cubic graph, we just want to keep in mind how if A is a negative, it will eventually just be going down. If A is a positive, it will eventually just be going up. So before we dive too deep into this, this is one very important idea with cubic functions. With cubic functions, one major idea is stationary points. So what you want to keep in mind is that with a cubic graph, let's just have one there to refer to. So with stationary points, right, in grade 12, we want to keep in mind two major kinds of stationary points. You have a local minimum and a local maximum, and then you have what we call a point of inflection. So just to go through those three: local minimum, local maximum, and then the point of inflection. So with our local minimum and our local maximum, those are basically your turning points. And with all cubic graphs, you will always have two turning points for now. So we know that with our turning points, we know that this will refer to that as our local maximum. This will refer to it as our local minimum. So our point of inflection is literally the point that is right in between your cubic graph, or rather it is the point that is right in between your two turning points. So what we mean by that is, if we have a cubic graph, right, we have a turning point over there, we have a turning point over there. So if you consider the x value of your one turning point, the other x value of your other turning point, the y value for this one, and the y value for your other turning point, the point that is literally in between them, right, this one, that's your point of inflection, right? So in simple terms, your point of inflection is literally the point in between your two x values of your turning points and your two y values of your turning points. It is the point on your graph where your graph basically changes concavity. If you check here, we know that there's like a mini hump there, and then just at this point, that mini hump is starting to make like a mini U. Okay, so that's our point of inflection. So the simple thing you also want to keep in mind is that working out your point of inflection, there are multiple methods to do so. Again, the one big idea you want to remember though is that your point of inflection is literally this point right in between your y value of your one turning point, the other y value, and then the 1x and the 1x, the point that's literally in the middle there, that's your point of inflection. So literally, if you had, let's say, the coordinate there and you had the coordinate there, your point of inflection would be the midpoint of those 2 points there. So just keep in mind stuff like that, because I've noticed in most textbooks they leave stuff like that out for reasons I don't know. But anyways, so that's your point of inflection, and these are the key things you want to remember about stationary points. So whenever you hear questions or you go through questions that ask you for stationary points, you want to keep in mind that they will either be asking for turning points, which are your local minimum and your local maximum. These are turning points. This, however, we said that's the point in between those turning points. That's your point of inflection. So that's for stationary points.